This last video for chapter 13 talks about the central limit theorem. So most population distributions are not normal, okay? What is the shape of the sampling distribution of sample means when the distribution isn't normal? Well, fun fact is that as my sample size increases, the distribution of sample means changes shape and it turns into a normal distribution, which is so nice. So if I draw a simple random sample of size n from any population with mean mu and a finite standard deviation, the central limit theorem says that when n is large, typically I think it's like greater than 30, the sampling distribution of the sample mean x bar is approximately normal. So x bar is approximately the normal distribution with mean mu and standard deviation of sigma over the square root of n, which is the sample size. And this central limit theorem allows us to use normal probability calculation, so we can bring back the z-table, whoop whoop, to answer questions about our sample means, and even when our population distribution isn't normal. This is nice. So let's look at an example. So based on service records from the past year, the time in hours that technicians required to complete preventive maintenance on an air conditioner follows a distribution that is strongly right skewed, okay? Remember that means the hump is on the left. So right skewed is kind of like this. And whose most likely outcomes are close to 0. The mean time is 1 hour and the standard deviation is 1 hour as well. Your company will service a simple random sample of 70 air conditioners, and you've budgeted 1.1 hours per unit. My question is, will this be enough? So the central limit theorem states that the sampling distribution of the mean time spent working on the 70 units has a sample mean, which is equal to our population mean, which is 1. So the standard deviation is going to be the standard deviation of x divided by the square root of n, which is going to be 1 over the square root of 70, which is 0.12, and it will have a normal shape. So we've got the normal curve 1.12. So let's look at our examples. Well, let's continue this example and look at some graphs. Let's visualize this. So A right here is the distribution of one observation. This would be the distribution of the mean for 2 observations. This would be the distribution of the mean for 3 observations. And here, 10. And this would be the distribution of x bar for 25 observations. So it is more and more normal, as you can see. So the sampling distribution of the mean time spent working is approximately this because our sample size is greater than 30. That's what I said it had to be for us to have like a big, large sample. Here's the exact curve density for our sample, and here's our normal curve, right? So I can use a z-table, right? So I budgeted 1.1 hours. So I take z is 1.1 minus 1 over 0.12. That gives me 0.83, and I need to take that into a z-table. So here's 1.1. We got to find this area. So I want the probability that x is greater than 1.1. That's going to be the probability that z is greater than 0.83. So 0.83 has a z-table value of 0.7967. And because the total area under the normal curve is 1, we have to subtract this to find this area over here, which I'm going to highlight in green. So I have 1 minus 0.7967 is 0.2033, so like 20%, right? So there is a 20% chance that the technicians will not complete the work within the budgeted time, that they will go over the time. So we've looked carefully at our sampling distribution and sample mean, However, any statistic we can calculate from a sample will have a sampling distribution. So here's the distribution of 100 sample medians instead of means for samples of size 5, and here's a distribution for 1,000 sample variances for samples of size 5 where variance is sigma squared. The sampling distribution of a sample statistic is determined by the particular sample statistic we're interested in. Typically, this is mean. 95% of the time, we're interested in mean. The distribution of the population of individual values from which the sample statistic is computed and the method by which the samples are selected from our population, right? We need them to be a simple random sample. We need them to be representative. But sampling distributions allow us to determine the probability of observing any particular value. And we said that an observed effect so large that would rarely occur is called statistically significant. And we're going to get bigger and more into detail about what's statistically significant in the next chapter. But let's quick consider the second graph on the previous side. We may decide, based on our observations of 100 samples, that because we see only 2 with variances above 200, that would be a statistically significant event, right? Like, so if we go back to our graph, so we've only got 2 with values over 200 all the way over here, right? We could say that those are statistically significant. Those are outliers. But we will talk more about statistical significance in chapters 16 and 17.